assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we want to determine what the induced EMF is in a conductive wire loop here in a uniform magnetic field when we change the strength of the magnetic field by 0.2 teslas per second, and we have an area of 0.018 meters squared for our loop. And once we know what the induced EMF is going to be for that situation, we're going to try to figure out by how much or by what rate we would have to decrease or increase the area of our loop at the same time this stuff's going on in order to cancel out the induced EMF from the first part of the problem. So for the first part, we said we're just looking at the induced EMF. So from Faraday's law, we know that the induced EMF is equal to minus the change in flux over the change in time, where the change in flux is just going to be the final flux minus the initial flux. Now, in general, our expression for the flux is just going to be B times A times the cosine of the angle between our magnetic field and the surface normal of our loop. And since we know that during this whole problem, that angle is 0 because those two things are parallel, the cosine of 0 is just 1, and really the flux is just B times A for the whole problem. So in this first scenario, since we're changing B, but not A, our final flux will be B final times A, and our initial flux will be B initial times A, but A is the same for both situations. So this means that our change in flux is going to be B final times A minus B initial times A, or if we factor out an A, we'll have A times B final minus B initial, and B final minus B initial is just delta B. So if we plug that back into Faraday's law, we'll have that the induced EMF is equal to minus the change in flux over the change in time, which is minus A times delta B over delta T. And if we're just looking for the magnitude of our EMF, we can drop the sign and put a little absolute value signs around our EMF. So we're looking for the magnitude of the EMF. And since we have delta B over delta T, and we have our area, we can just plug those values in and solve. And if we do that, we'll get that the magnitude of the EMF is 3.6 times 10 to the minus 3 volts. All right. So now in the second part of the problem, we're imagining that we're shrinking or enlarging our loop at the moment when our magnetic field is equal to 1.8 teslas. And we're going to try to exactly cancel out the induced EMF from the first part. So we want to shrink our area or increase our area in such a way that we end up with an EMF of magnitude 3.6 times 10 to the minus 3 volts. And we want to find at what rate we're going to have to do that. So we're looking for delta A over delta T. So again, we're just going to consult Faraday's law, specifically the magnitude of Faraday's law. Where now our change in flux is going to be B times A1, or sorry, A final, minus B times A initial, since the field is going to be the same during this rapid change in size, but the area will change. Or if we rewrite that by factoring out B, we'll have B times the change in area. And again, if we plug that into Faraday's law, we'll have that the induced EMF is equal to B times delta A over delta T. And we can solve now for delta A over delta T just by dividing both sides of this by B. So we'll end up with delta A over delta T is just the magnitude of the induced EMF from part 1 over B. And if we calculate that, we will get 2 times 10 to the minus 3 meters squared per second. Okay. So that's how fast we would have to change the area of our loop to counteract this induced EMF from the increasing magnetic field. So now the question is, do we want to shrink our loop or do we want to enlarge our loop in order to cancel this field out? So let's go ahead and use our picture as an example here to help us along. So in this picture, the magnetic field is pointing into the page and it's increasing into the page. So the flux is increasing and B is into the page. So if the flux is increasing into the page, we will want to create a magnetic field that points in the opposite direction to try to counter that out. And to do that, we'll need a counterclockwise current. Because if we point our thumb in the direction of the field we want, right, which is out of the page towards us, and curl your fingers around, they should curl in the counterclockwise direction. So there's the direction of our induced current, and we know that it's pointing out of the page. So now, in order to create a current that goes in the opposite direction as this one, and creates a magnetic field in the opposite direction of this induced current, we will want to shrink the loop, because we can see if we shrink the loop, we will have a decrease in magnetic flux into the page. And since there's a decrease into the page, we will want to create a magnetic field in the same direction into the page. So we will want to shrink the loop. So maybe an easier way to think about that too is imagine if we just we're trying to create a net flux of 0, right, in order to have no induced EMF at all. Well, if in the first part we're increasing the flux through the page, then we just want to decrease the flux. And the easiest way to decrease the flux is just to shrink our ring. So there you have it. We figured out the induced EMF in our circular loop here as we change the strength of the magnetic field. And we figured out the rate at which we have to shrink our ring in order to cancel out that induced EMF entirely.